In this video, we want to be able to calculate whether salt solutions are basic if they're formed from the salt of a weak acid. That is, HA, a weak acid, can interact with water to form hydronium plus A minus, and A minus is the conjugate base of the weak acid, which could also be the anion in a salt, okay? Now, what we're going to discover is that Ka times Kb of its conjugate equals Kw. And because there are also tables of weak bases, I'm going to use prime, so Kb prime, to represent the conjugate base. So I could go to a table like table 16.31 of your Liber text, and in this table are a bunch of Kas for weak acids. Here's acetic acid, arsenic acid. And knowing that, I can calculate the Kb of the conjugate base. For example, acetate. Sodium acetate is a basic salt. Okay, so let's calculate this. First off, if this represents the equilibria, I could ask myself, what is the equilibrium constant? And for a weak acid, Ka is equal to the hydronium ion concentration times its conjugate base divided by the weak acid concentration, and we omit the water because its concentration is so high that it is essentially constant. Now, the A minus can also react with water. So both HA can react with water and A minus can react with water. And when A minus reacts with H2O, it forms the weak acid plus hydroxide. So the anion grabs a proton from the water, forming HA. And because this is the conjugate, I'm going to say Kb prime. Okay, and most folks don't use the symbol prime here, but realize we have tables of Kb's. And we typically don't tabulate the Kb of a conjugate, we tabulate it of its acid. Now, this Kb is equal to HA times OH minus, all divided by the initial anion. And that anion could have come from a salt. So if this had been acetic acid, I could have had sodium acetate, the salt of acetic acid. Okay? Now if I multiply these, I have Ka, Kb prime here. And I'm the only one who uses primes, as I said earlier. And I'm simply using the prime to indicate that this is the Kb of the conjugate base of the weak acid. And they must be for conjugate base pairs, acid-base pairs. So I have hydronium ion concentration times the A minus all over HA. Here is my Ka right here. And I'm multiplying this by the Kb, which is the HA over the hydroxide all over the A minus. And now I note that the A minus over A minus cancels, the HA over HA cancels, and I have H3O plus times hydroxide, which is Kw, which is 10 to the minus 14. Now this is important, because what this is saying is if I have a table of Kas, I can calculate the Kb prime of its salt. So Kb prime is equal to 10 to the minus 14 over Ka. So going back over here into the Liber text, I have here a table of Kas for weak acids. And every one of those weak acids has a conjugate base. And the conjugate base of that weak acid is simply 10 to the minus 14 divided by the Ka of the weak acid, okay? So this table here is actually two tables in one. It's a table of Kas and Kb's. And so, for example, if I had sodium acetate, okay? Sodium acetate, sodium comes from a strong base, so it does not interact with water. Acetate comes from a weak acid, therefore it interacts with water, forming the weak acid, and its Kb prime for acetate is 10 to the minus 14 divided by Ka of acetic acid. Okay? Hopefully this helps. Therefore, sodium acetate is a basic salt, its pH is greater than 7.